So the modular group, since it is isomorphic to a free product, it acts on a tree. I'm going to construct that tree from PSL2Z itself, and it will be slightly more refined, more than the versions that you may find in the literature. So from PSL2, starting from this, I am going to construct a tree such that the set of edges of my tree is just identified with PSL2Z. So for each element of the group PSL2Z, I have an edge of my tree. Well, for the moment, in fact, it's a graph. And vertices of F comes in two types, which I denote like this, and V, F. So type vertices of these two types are sets of pairs W, WS, where W is an element of PSL2Z. So these are left cosets of the subgroup IS, and there's another type of vertex which is of the kind W, WL, W square. So this is a triple such that W is in PSL2Z. So, well, there are edges, there are vertices, but I have to define also the incidence relation, and it is as follows. Two vertices V prime are joined by an edge if and only if V intersection V prime is non-empty. That is to say, I take two vertices of this type, and there is one such vertex. There is an edge between these two such vertices if and only if the intersection of these two sets is non-empty. And in this case, non-empty, whose element is the corresponding edge joining V and V prime. So, for example, I have a vertex of type W, WL, WL square, joined by, if you call this W, WL, WL square. So I have an edge of type WL, WL square, excuse me, WS, WLS, and here WL square S. So the incidence relations is like this. You can see that these two have a non-empty intersection, which is W, and that W is precisely the vertex between, precisely the edge between these two vertices. Similarly, these two has a common element, WL square, which is the name of the edge between these two vertices, and so on. More generally, I can construct my tree as follows. I start from the edge, which is named identity element of the modular group. So one and is I denote like this, the other like this, and so this tree is not just a tree, it comes with an extra structure. That is to say, whenever I have such a vertex, I can orient them in a fixed direction. I take this direction to be W, WL, WL square. So for each vertex of degree 3, I have a fixed cyclic ordering of that vertex, which endows with this cyclic ordering, endows my graph with what is called a ribbon structure. So here we draw the graph in such a way that these directions are, the L corresponds to turning left and L square corresponds to right, so that we can, the orientation defined by the table and the orientation given by this definition are compatible. So I imagine that I'm going from this direction to here, so I call this L. Here I call this L square, and this is L square S. LS here, LS, LS, L square, LS, LS here, L carré S, L square S, L square S, here L square S, LS, and I do the same thing in the opposite direction. This is S. This times this is LS, this is L square S, and so on. So this incidence relation gives me this tree, and this cyclic ordering of the vertices gives me this embedding of the tree on the plane. Well, a priori, we don't know that this is a tree because we can do this for any presentation of some group. However, in this case, this is a tree since, first of all, it must be connected and it must have no loops, since PSL2 Z generates is generated by the elements S and L. This is connected, and since it is freely generated by these two elements, it has no loops, so it is tree. F is a tree. I hope that the construction of the tree is clear. Moreover, this tree comes with an action of the group PSL2Z. I see that my space is even more constrained this time. So PSL2 Z acts on this tree by ribbon graph automorphisms. What does it mean, ribbon graph automorphisms? it means that this tree has a certain embedding of the plane, and I'm not allowed to change that embedding. For example, and so this tree has many automorphisms. For example, I can fix this part of the tree. I can fix this part of the tree. I can cut the plane like this and like this, and I can shift this branch like this and this branch like this. This is going to define me an automorphism of the tree. But this automorphism will change the cyclic ordering of vertices emanating from, of edges emanating from this vertex. So this is not a ribbon graph automorphism, okay? In general, this tree has many, many automorphisms. It has uncounted many automorphisms, and I described you just one of them. You just fix this, and another idea is to rotate this. I mean, you fix this part of the tree, and you rotate this part of the tree like this. This will give me another automorphism, which will also modify the cyclic ordering of edges emanating from this vertex. So this is not a ribbon graph automorphism. What is a ribbon graph automorphism? It must respect the tree and its embedding on the plane. And for example, one such thing would be to shift everything in this direction. That would give me a ribbon graph automorphism of the tree. So ribbon structure is just this. A cyclic ordering of every set of edges emanating from a vertex. So since these vertices are of degree 2, it doesn't matter which ordering I give. However, for vertices of degree 3, I fix this ordering. So if I, for example, change this branch by rotating this branch like this, then I change this cyclic ordering. So it is not a ribbon graph automorphism anymore. It is a tree automorphism, but it is not a ribbon graph automorphism anymore. So let us concentrate on this action a little bit. So how does it act? The action is by M in PSL2Z sending. So it must, first of all, I must define automorphism of the tree. So it is from EF to EF and sends the edge named W to the edge. I don't need to put this inside braces. So the edge named W to the edge named MW. So it also defines, it must also define a map between vertices to be an automorphism. So it sends the vertex WS to the vertex MW, MWS, and the vertex WL square to the vertex MW, MWL square. Okay, so let's see what is the simplest automorphism. For example, if I pick S instead of W, then this automorphism will send WWS to SWS, and this vertex to SW and SWL square. So let's see what happens here. So this, first of all, the edge named S is sent to the edge named I, n'est-ce pas? Isn't it? So we have an edge named S, it is sent to. So if I put, well, to start with the simplest thing, if I put W equals to the unit element I here, then this is sent to S times I, which is just S. This edge I is sent to this edge. And correspondingly, this edge S is sent to S square, which is just identity. So this element is sent to this element. Now, what about this? What about the edge L? So, again, by definition, the edge named L is sent to the edge named S times L. Where is S times L? So this is sent to here. And what about the edge named LS? It is sent to the edge named SLS. And the edge named SLS is here. So this edge is sent to this edge. And whatever, what about, there's something strange. Oh, yeah, this must start with S. This also must start with S. So LS is sent to SLS, okay? Just a minute. I did something wrong. So this is. Perhaps I did something wrong with the initial tree. L, LS. I think I did something wrong. Let me think a little. Yeah, what I did wrong is that I wrote these letters to the end, whereas I should have written them to the front. So this should have been L, and this should have been SL. Okay. So this is right. So up until everything is correct. So this is S time L. This is S time L square. This is L square SL. This is L SL. This is LS. This is SLS. And this is L square S. This is S L square S, etc. Okay. This is how they are connected according to the definition I just wrote here. And now we can reconcentrate on the initial action. So S is sent to I, and I is sent to S. And L is sent to just S times L. Again. Did I write the same thing? I'm just confused. This should, yeah. I think I wrote the same thing. This should be L times S. Should be I think that now it is hopefully correct. L square S, so this should be S L square. Should be L S L square. S L square S. And this should be L square S. So what this automorphism does is that it sends L to SL, LS to SLS, and SLS to, it will rotate this like this, SLS to, it will pre-multiply this by S, so it will SLS, send SLS to LS again. And SL2, if you multiply this from the left by S, it will go back to S. So we see that this automorphism of multiplying everything by S, the automorphism corresponding to S is the rotation of the tree around the vertex I S by 180 degrees. So this rotation is just rotates the tree. And if we do the similar thing for the automorphism corresponding to L, we see that it is the rotation by 120 degrees around the vertex I W square. And we know that the group PSL2Z is generated by these two elements. So any, in general, automorphism coming from this PSL2Z action can be written as a sequence of rotations. So we rotate in this way, and then we rotate this around this vertex, and then we rotate around this vertex again, and then we rotate perhaps twice or once around this vertex again, and we get any automorphism. We can obtain any automorphism coming from here. And in fact, these will give us all the set of all ribbon graph automorphisms of the tree. This gives all ribbon graph automorphisms. This also shows that the action of the tree, the action of PSL2Z on the tree is not free. It has some fixed points. Already these are rotations, S and N are rotations, so they have the corresponding fixed points. This rotation has this fixed point, and this rotation has this fixed point. And in general, if I, so WS is sent to MWS. So if I multiply this by WS, so if I write WS W minus 1 instead of M, then this goes to WS W minus N W, comma WS W minus S WS. So after simplifications, these two cancel each other, and these two cancel each other. So this is sent to WS W, which is the same vertex as before. So in general, the vertex WS is fixed by the automorphism coming from WS W minus 1, and similarly WL W square is fixed by WL W L minus 1. So the action has many fixed points. The action is not free. And we are going to come back to this non-freeness of the action later. But let us now turn back to our initial question of parameterizing all real numbers as the boundary of the group PSL to Z. And let us construct some simplistic approach to the boundary of the modular group. So in fact, I must define what an end of a group or end of a topological space or end of a tree is, but I'm not going to do that. Instead of that, I'm going to give some more rather direct definition. Denote by del F the set of all infinite non-backtracking paths in F that start at the identity. So what does this definition mean? We consider a path starting from identity here and going towards infinity. I put this condition non-backtracking to avoid strange things such as paths coming here, coming back, going here, coming back infinite many times, and not leaving this edge anymore. So in order to avoid such things, I don't want my path, infinite path, to do backtrackings like this. It must continuously go towards infinity. So the set of all such paths is called the boundary and denoted by del F. And we can represent the elements of the boundary as infinite words ls to the power n0. So it is going to be, what is written here is going to be a longer and longer word. So L square S L square goes like this. And so each infinite path, for example, going like this, can be written as an infinite word. In this particular case, it is going to be L S, here it must be L square, and L square, L S, L square S, and so on. So this path, let me draw this by yellow. This path can be encoded as an infinite word like this, and in general, any infinite path in the tree, starting from identity without ever going back, can be encoded as a word in n1, and then ls to the power n2, and so on. And for the moment, I consider only paths which live here, which I denote as del F plus. And we also see that the group PSL to Z just as it acts on the tree, it acts on the set of such paths by precomposition. That is to say, an element of PSL2Z is a sequence in L and S. We can put it here, and we obtain another path of the same kind. And this is a well-defined group action on the boundary of 3. In fact, this boundary is endowed with the product topology. That F is endowed with the product topology. Which can also be given as a metric. And the topology says that two paths are close if they go together for a while. If they go together for a longer time, then they are closer. So a neighborhood of this path, for example, consists of all paths which diverge from here. So for example, all these paths gives us a neighborhood of this path. And if I do same thing here, it gives us a smaller neighborhood, etc. So the boundary is a topological space. And well, let me also write this once more. Ls was 1 plus x, so that Ls to the power n is n plus x, and L square x is x over 1 over x, which is 1 plus 1 over x, so that L square s to the power n equals 1 over n plus 1 over x. Now we consider the map. There is one more thing that I would like to say about this boundary. In fact, del F is a cyclically ordered topological space. Why is this called the product topology? Because, well, one explication is that if you concentrate only on the right-hand side, then you can identify the set of paths on the right-hand side by the set left, right to the power infinity. So left means turning left, right means turning right. In fact, here L squared means right, okay? So this is just left, right to the power infinity. If you impose the product topology, it's exactly the same topology. And you have two such things glued to each other. So we consider the map from this part of the boundary to the set of positive real numbers, sending L s to the power n0, L square s n1, ls n2, etc., sending this element to n0 plus 1 over n1 plus 1 over n2 plus etc. If indeed you compose these operators, ls to the power n0, L square s to the power n1, etc., you indeed end up with this continued fraction. So we consider this continued fraction, and the claim is that this is almost a homeomorphism. It would be a homomorphism, but it has a little problem that it is not one-to-one. It is 2-to-1 on the set of rationals, and 1-to-1 on the set of irrationals. So here there is a catch. The boundary elements L0 to the power N0 L square S etc. until Ls to the power Nk plus 1 and L square plus infinity and Ls to the power N0 Ls to the power Nk L square S Ls to the power infinity. So why do I have Ls to the power infinity here? It means that this designates a path which always turns right after some point. And this designates a path which always turns left after this point. For example, this path is a path which always turns left after this point, and this is a path, no, this always turns right, and here this path always turns left after this point. So here, at this point it turned left, but after turning left, it always turned right, and here in the beginning it turned right, and after this it always turned left. So the first situation corresponds to this, and the second corresponds to this. So these boundary elements corresponds to the continued fractions, are sent to the continued fractions. This one is sent to the continued fraction N0 plus 1 over plus Nk plus 1, 1 over Nk plus 1, and this is sent to the continued fraction N0 plus 1 over Nk plus 1 over 1. And these two numbers are same. So this map is one-to-one on the set of, this is a claim that in fact I have to prove, but I am not going to do that. This map is one-to-one on the set of irrational numbers, and it is 2-to-1 on the set of rational numbers. And this 2-to-1ness is just this, because every rational number admits two simple continued fraction representations, which is this and this. I hope that you see that these two give equal numbers, right? These two give equal rational numbers. So this fact is similar to, you know, in our decimal system also, some numbers have double representations. The numbers having infinite, ending with infinitely many nines are same as numbers ending with infinitely many zeros. So continuous fraction representation also has the same problem. It has this double representation. And this double representation means that, in fact, so since every infinite path starting from the identity represents, on the tree, represents a real number. Okay? Uniquely, if these paths are not of this kind. If it, from some point on, if it always turns in some direction or in other direction, they represent the same rational number. In this case, these two paths represent the rational number 1. So, and this is only in the case k is even. If k is odd, then I have to exchange these two, L squared with Ls. However, it is essentially the same, so I'm not going to write this again. Okay, what about the left-hand side? So I could parameterize all rational numbers and real numbers by boundary elements. That is by infinite words in the modular group. What about the left-hand side? In order to handle this, we consider the map kappa, which goes from the boundary of 3. So the boundary of the tree is the same notion here as the boundary of the group itself. R union infinity, which is defined as, this is the continued fraction map. So this is sent to the continued fraction n1, n2, etc. if x does not start with an s, l squared s to the power n1 and so on, and minus 1 over n0 n1 if x starts with an s. So this is not a homeomorphism again. However, this way I could parameterize the real numbers as well. So the rational numbers in general, negative and positive, are they correspond to infinite paths which turn always right or which turns always left from some point on, and real numbers corresponding to paths which are not of this type. So, as I said, this is almost a homeomorphism. In fact, by applying a standard topological procedure for such situations, I can identify the fibers over which this function is not one-to-one and obtain homeomorphism. That is to say, I can introduce an equivalence relation on the boundary, and this equivalence relation will identify these two paths. Okay, this is a point in the boundary, and this is another point on the boundary, and I consider the equivalence relation which identifies this. So it does the same thing for all such points, and I can, since there's a topology, a product topology on this space, I can quotient this with this and obtain a topological space. And in fact, this topological space is just isomorphic to the circle, homeomorphic to the circle via the map kappa. So this was my promise. I promise you that the modular group is really exceptional in that it has a simple presentation, really simple presentation that I could show. And I told you that, I promised you that I'm going to show you that the modular group parameterizes all comparison processes, antiphyresis processes, and I think that I could have shown that also. So in a rather very beautiful and seamless way, we see that via continued fractions, such infinite words in the group PSL2Z, they parameterize us all comparison processes, and these comparison processes correspond to all real numbers in a rather natural and beautiful way. And, well, does this fact require a proof? Yes, but the proof is, for me, is really simple because, well, how to prove this? The proof depends on the following fact and infinite. Once you identify the finite paths via continued fractions by rational numbers, then every infinite path is nothing but a Dedekind cut. Because as I mentioned, this is an ordered topological space. So it makes sense to speak about Dedekind cuts. And, well, this is the idea of proof, that this thing is a homomorphism. So how does this identification go? There's a very nice way of identifying these things with the rationals, these pairs of ends with the rationals. Let me conclude my talk with that. So I consider only the positive part, and the negative part of the tree lies above. So here, this is the identity. Identity times S lies above, and here it goes. And, well, here I write 0 over 1, and here I write 1 over 0. And to obtain the rationals corresponding to these regions, recall that this path and this path correspond to the same rational. So I can say that, in fact, this region corresponds to a rational, because these two paths determine the region. So in order to find the rational corresponding to this region, we just add these two in the wrong way. That is to say, we do the Ferry summation, P over Q sum R over S equals P plus R over Q plus S. If you do that, here we get 1 over 1. So in order to find the rational corresponding to this region here, we sum these two, which will give us 1 over 2. To obtain the number corresponding to here, we sum these, and we get 2 over 1. And we continue in this manner. So here it's going to be 1 over 3 to obtain the rational corresponding to this region. I sum these two, and I get 2 over 3. Here I get 3 over 2. Here it is 3 over 1, etc. Of course, here I omitted the vertices of degree 2. That's to say, so these are vertices of this type. And etc. Okay, this is all I want to explain for today. Tomorrow, I'm going to talk about the subgroups of the modular group. In fact, this is a really, what I'm going to explain is really something very basic from topology, the corresponding between coverings of a topological space and the subgroups of its fundamental group. Usually, this correspondence cannot be made very explicit. However, in our case, we have a group acting on a tree, and the corresponding object spaces are very simple, so that we can make all this story very, very explicit. And we are going to describe we will be able to describe all subgroups of the modular group as quotients of the tree under these subgroups. And I hope that it will be illuminating from some points of view for some of you. And, well, thank you very much for your patience for today.